Hello, good morning, good afternoon, or good evening, any time of the day you may be watching this. This is a lecture on numerical integration for undergraduate class. Before I delve into it, I want to advise that you subscribe to this channel because subsequent lessons will be posted herein. Now let's go. Some functions are difficult or hard to evaluate. Functions like sine of x squared or e to the power of x divided by x cannot really be integrated or evaluated analytically, but can be done numerically. That's the purpose of this class. To see how functions like this can be evaluated. Two methods are commonly used in solving these types of problems. We have the trapezium rule and the Simpson's rule. Trapezium rule and the Simpson's rule. This is the Simpson's rule and this is the trapezium rule. Trapezium rule. First, let's look at this figure. This y, this x, this curve is actually y of x, or y equals f of x, as the case may be. Finding the area under this y of x is actually the integration of this function. From x of a to x equals to a to x equals to b. So that may be talking about the lower limit a and the upper limit b. So the area under this curve y of x is actually the integral value of the function y of x. So for a function like we mentioned earlier that cannot be integrated analytically with a conventional formula for integration, we wish to evaluate this integral from a to b of y of x dx. The required area is divided, for trapezium rule now, is divided into n strips. As you can see in that figure, each of the strips has a width of h. You can see here as well that taking each of those strips you can see become actually trapezium. This is trapezium, this is trapezium, this is a trapezium. Both of them have two sides, y of I and y of I plus 1 here, and then width of h. That is to say, each strip is approximated by trapezium. And we can see that h here is equal to b minus a divided by n, where n is the number of strips. The area of the trapezium, as we know from our elementary mathematics, is the two sides, sum of the two sides divided by the sum of the two sides multiplied by h divided by 2. Half h, a plus b. That is the conventional, that we know, the formula for finding the area of a trapezium. So for this figure now, summing up the areas of all the trapezia that we obtain by dividing the curve into strips, we have this. This is what we have when we sum up all the, and then the sum of this trapezia is equal to the integral of the function that we are supposed to find the integral of. Note, if the number of strips is increased, h is decreased, then the accuracy of the approximation is increased. What we're actually doing in numerical integration is finding estimate. It's actually an approximate solution or an estimate value of the integral we are finding, not the exact. That's why it is actually numerical integration. So let's have an example to solve. This is an example. Use the trapezium rule to estimate integral from 0.5 to 1.3 of exponential x squared dx using a strip width of 0.2 and a strip width of 0.1. Solution. Firstly, we tabulate. We are given the upper and the lower limit of the integration, and we are given the strip width. So for the first one, a, strip width of 0.2. We now begin to list under the column of x from 0.5 to 1.3 with the width of 0.2 h, 0.2 to 0.7 to 0.9 to 1.1 1.3. We now find the corresponding value of the exponential x squared for each of the x. For 0.5, y becomes 1.2840 down the line like that. Then of course, we have been told h is 0.2, as you can see from that. Now, some of the areas of the trapezia, we have this. The first term is retained. The last term, y of 0 and y of n, the last y of n, that's y of 4 here, are retained, while the others are multiplied by 2. That's what we have. So these 2 times this, 2 times this, plus this one is not multiplied by any scalar. So we now have 2.117 as the sum of areas. Therefore, the integration or integral value of e of x squared, e raised by x squared rather, the x, from 0.5 to 1.3 is approximately 2.117. B, the other part of the example, as in A, you list the values of x and corresponding values of e to the power of x squared, but now using h to be 0.1. You approach it the same way, list x, corresponding value for y, x from x0 to x8, from y0 to y8. So from this table now, for using trapezium rule as usual, 0.1 to 2, this h is 0.1. You do the same thing we did for the fourth example. It's the same thing, but the strip width is different. So automatically now have the integral 0.5 to 1.3 of e raised to power x squared dx is approximately 2.085. From this example, we can see that dividing the interval 0.5 to 1.3 into strips of width 0.2 results in a more accurate estimate than using the strip of 0.2. Use strips of 0.1 gives a more accurate estimate than using the strip of 0.2, because 0.1 is shorter. The width is shorter than 0.2. That's why the result seems to be more accurate in estimate. So then that is what the trapezium rule actually entails. Let's quickly go through the Simpson's rule as well. Simpson's rule is also a method for solving numerical integration problems, but instead of having the curve divided into strips of particular width, we estimate the curve by a series of quadratic curves. The area under the curve is divided into an even area. It's an even number of strips of equal width. Like this equal even number 1, 2, 3, 4 even number of course width, but they actually they do not form trapezium here. That's what they're talking about. You do not deal with trapezium here because they're dealing with a quadratic curve. They are dividing the curve, the original curve y of x, into. This is what Simpson's rule states. You can see it's now instead of dividing the h by 2, because it's a curve, divide the h by 3. That's why we have this, and we have this as the general formula for using Simpson's rule to solve integration problem. You can see for the even entry, for the odd entry, y1, y3, y5 multiplied by 4. For the even entry, y2, y4, y6, y8, we multiply by 2. And then the first and the last terms, y0 and yn, are retained as they are. Note, even number of strips is used in Simpson's rule, unlike what we have in the trapezium rule. Let's quickly see an example. The same problem we solved with the trapezium rule, let's solve it with the Simpson's rule. For now, A, 4 strips, B, 8 strips. Let's note, for the trapezium rule, we are given strip width. Here, we are given number of strips. Let's go on. Solution. As usual, let's tabulate. X, y equals f squared. Here, n equals 4. Number of strips equals 4. H will then be b minus a over n, or b minus a over 4, or 1.3 minus 0.5 all over 4. You remember, at the beginning, we said relationship between h and n, number of strips and strip width, is h equals b minus a all over n. So this gives us a strip width of 0.2. We do it the same way we did the trapezium. We tabulate, get corresponding value for y, and then estimated value, get the sum of the areas there. This is, you do the same thing, but you have 4 for the odd entry, 2 for the even entry. The same thing give us approximately 0.762 as the estimate for the integral e x raised to power x squared. So for b, for the other part, we have n equals to 8. Number of strip is 8. Therefore, our h is 0.1, just like we did before. So we tabulate as usual from 0.5 to 1.3. But because h equals 0.1, can see the entries for x, they are more than what we had for the h to be 0.2. That is to say, for the strip width, or sorry, number of strips to be 4. So we have to tabulate the same way, and then we have it this way. Our estimated area is this. Therefore, the exponential, the integral for exponential of x e to x squared gives us approximately 2.075. This is an exercise for us to solve using Simpson's rule that we have just discussed. This is an exercise for us to look at. Let's look at it, and that'll be fine for us. These are exercises. These are exercises. All right. So this is another exercise, and this is also some practice exercises for you to do. So this is the end of the class for teaching us on Simpson's rule and the trapezium rule for solving numerical integration problems. Once again, try and subscribe so that I get subsequent lessons from this same channel. For now, I say have a great day.